Hello again and welcome to part 2 where we're looking at the new Brymen BM786. That's the meter in the center here. Currently I have all my Brymen meters out. What I'd like to do is run these all through the same test where we look at the DC voltage off of this test box. So we're going to start with this little pocket meter. This meter is actually sat outside during an entire winter. You can see it's currently in the DC volt mode. Let's just see, so 47 volts DC, and let's see what we get for AC. Looks like about 68 volts AC. Again, let's go back to DC. Well, frequency should be roughly, again, 3 kilohertz. Looks like it can't pick that up. Probably requires a zero crossing. But you can see it definitely is able to read a DC voltage off of this test box. Okay, before we move to any of the other meters, again, let me just refresh you as far as what it is that we're seeing. We'll place the BM786 in its DC volts mode. And again, let's go ahead and turn on the power. And you can see it's reading roughly 4.4 volts DC. And again, if we manually range the meter, there you go, 57.8. And if I place it back into AutoRange, again you can see it reads basically 4.5 volts or so. So let's try another meter. This is the Brymen BM319S. This is their automotive meter. And again we'll place it into the DC volts mode. And let's see what we get. So 58 volts. Sorry about the glare. So yeah, 58.2 volts. Let's just try it in AC. And it looks like about 67.5. And again we go back to DC, 58. See, it has no problems displaying that at all. Let's try the BM235. And again we're in DC volts. And there you go, 58.3. Let's go to AC. Oh, it's in VFD mode. So 42.7, and again go back to DC, 58 volts. Again, this waveform's kind of complex. It is a square wave. This is the Brymen BM839. Let's see if the batteries are still good in it. Oh, looks okay. It's in AC mode. Let's just give it a try. And here we go. So it looks like 3.2 kilohertz, that's about right, and 65 volts. And again, let's just try it in DC. Here you go, 62 volts. No problems at all. Last, we have the Brymen BM869S. So this is the one that I changed the microcontroller out in the other day. And let's just see what happens here. So again, 58.4 volts, 65 volts at 3.2 kilohertz. Then we can go back to DC, and again no problems at all. So this is the original meter I purchased. The way I can tell the difference between the two is you can see that TME had added these additional stickers to the back of the meter. This meter is basically all original. So again, let's just go to DC volts, and let's see, it displays 58.58, and let's go to AC. Again, 66 at 3.2 kilohertz. So the only meter that seems to have a problem with looking at this is our new meter. And again, let's just go ahead and attach it, and we'll go to DC volts. And there you go. So 4.4, 4.5 volts. Let's just change the polarity of the two. And here you go, negative 2.8. So I'm not sure what the problem is. I suspect it has something to do with the square wave. Again, it's kind of an odd problem if we were to take and load this down a little bit. So again, the other day we just used this 100 picofarad cap. Again, let's just place that directly across the inputs of the meter. You can see the meter will read correctly at roughly 60 volts. And again, one of the things that we had noticed is if we change that value, basically by having more meters installed, let me just grab a different capacitor, and we should actually get a different voltage. Again, it's going to change the loading on the box. So let's just try it. There you go, so 98 volts. So I think all it is, again, is that it's just something about this being a square wave, in that the meter just doesn't like the higher frequency. I'm not really sure. I haven't seen a meter before that didn't work with this test box. Normally I just rifle right through it and everything is just fine. So it's a little bit of an unusual case. Hopefully we can figure out what's wrong with it. Again, it's very possible it's something that I'm doing wrong. Currently all the Brymen meters are attached in parallel. I've left off the pocket meter because I'd have to kludge something up in order to clip into the leads. To the left here you can see I have our high voltage power supply out, and I've got our high voltage probe that's attached to the last meter in the chain. The oscilloscope is set for 500 volts per division. You can see it's dancing around the 0 point, so essentially the center line here, this is 0 volts. Let me just turn that up a little bit for you. So let's go ahead and we'll just give it some bias. So it's about 150 volts or so. It's about 280 volts. Tell you what, let's change our scale. So now it's 500 volts per division, and let's go ahead and double the voltage coming out of this thing. And you can see all the meters are reading roughly 318 volts. Alright, so I've adjusted our frequency up. This is currently running at 4 kilohertz. You can see 4 kilohertz. And again, if we manually range the meter, there you go, 190.71, right on par. Let's just go back to auto, and again, let's just change the bias a little bit, or we can double it, cut it back in half. Again, let's pull it negative. This is about negative 280 volts or so. Again, we can double it, so there's negative 560. See, again, I'm not really sure what the problem is. I suspect it has something to do with me driving these with a square wave. That's basically what our other test box does. What I'd like to do eventually is I've got a power amplifier, and I'll hook that up to the ARB, and then what I can do is apply some predefined waveforms to all the meters and basically see how they all respond. What I'd like to do first is give Brymen a chance to reply to this. It's very possible it's just something I'm not understanding about this particular meter, and if it seems like it's nothing that they're too concerned about, what I'll do then is go ahead and set that test up and we can run it. What I don't want to do is basically take a lot of time running the test and then find out they've got a fix for this thing, and then we have to repeat the whole test again. So I'm going to ignore this problem for right now, and we'll just continue on with our testing. You can see the BM786 is set to its millivolt DC function. This is currently attached to our Fluke reference. We're applying 1 millivolt. This is inside of our temperature box. What we'll be doing is looking at the temperature drift. So again, there's a camera located inside the box. It's pointed at the face of the meter. And so here's our setup. I basically have a small power supply that's used to drive a couple of Peltier junctions. There's a fan here that's just blowing air across our heat sink. This all runs off a lab view. To monitor the temperature, there's an RTD that's located in the center of the box. I've had our temperature chamber set at -5 degrees Celsius. It's been below 3.4 degrees Celsius for a little over an hour right now. You can see it's just starting to regulate. The office temperature is a little warm, so it's having difficulty getting down that cold. Looking at the voltage on the meter, you can see it's 1.04 millivolts. So it looks like it's drifted about 0.04, maybe 0.05 millivolts. Let's go ahead and we'll change our set point. Alright, so it looks like it's reached about 0.91, 0.90 millivolts. I've seen a lot of meters that have drifted a lot more than this one. Let's just bring the temperature back down to room temp. Currently all these meters are attached in parallel and they're connected to my function generator. You can see I'm applying 1 volt RMS. This is currently at 50 Hertz. You can see that here, 50 Hertz, and also up on the X-Tech meter. What we'll do now is go ahead and increase the frequency, and let's give you an idea of what the roll-off of this new BM786 is compared to these other meters. Alright, so currently you can see we're at 10 kilohertz. You can see our sum is fairly close to the 3 dB point right now. Let's go ahead and we'll increase it a little further. Currently we're at 12 kilohertz, and I think this is where the BM786 is going to start to roll off. What I'm going to do is just increase it by increments of 1 kilohertz right now, and just pay attention to how this thing rolls off. This is 13 kilohertz, 14 kilohertz, 15, 16, 17, 18, 19, 20, 21. So yeah, about 21 kilohertz is the 3 dB point for this particular meter. We'll go ahead and let's just take it up a little higher. So here's 22, 23, 24, 25. Here we're at 31 kilohertz. Here we're at 40 kilohertz. There's 50, 60, 70, 80, 90, 100, 200 kilohertz. You can see our flukes now starting to roll off. 300 kilohertz. 400 kilohertz. You can see the BM786 now is rolling off. This is basically its 3 dB point. 600 kilohertz, 700, 800, 900. Here we're up at 1 megahertz. I would imagine most people, if you're working in a megahertz or even several hundred kilohertz, you're probably using an oscilloscope, not a handheld meter. Alright, so all the meters are still attached in parallel and they're connected to the function generator. You can see I'm outputting a 100 kilohertz waveform right now. This is actually a sine wave, and it's a 10 volt peak to peak. So both the unity and the sem meter are set to their frequency modes. I have the 189 just set to its millivolt range. I'm also using the millivolt for the 2 Brymen meters. And then for our TPI 194, I have it in volts AC displaying frequency. So you can see they're all basically displaying 100 kilohertz. Let's go ahead and we'll increase the frequency. So we're currently at 1 megahertz, and you can see the 189 can no longer read this. And even in the voltage mode, you can see it can't read this. So we're way beyond the upper limit of what this meter can read. Let's go ahead and we'll increase it. And you can see we're now at 4 megahertz, and it looks like the BM786 is no longer able to read it as well. But you can see the BM786 isn't having any troubles with this at all. Let's go ahead and we'll take it up a little higher. Here we're at 6 megahertz, and you can see the 194 is also dropped out. Let's go up a little higher. Alright, and here we are at 7 megahertz, and you can see the 786 is now dropped out. I wouldn't imagine that most people are going to use a handheld meter for a frequency counter. If you are, one thing, you're probably not using these leads. Meters aren't typically going to be very sensitive as well for picking up frequency. You may require some additional gain in order to be able to use your meter. I've demonstrated that in the past where I've basically taken some power amplifiers and driven them into the meter's front end to basically see what the real upper limits were. Let's go ahead and we'll just increase this a little further. Here we are at 10 megahertz, and you can see the sem meter is no longer able to read this as well. I think the sem can actually go up quite a bit higher, but again, it would require some type of amplification for you to use it. So in this particular test, you can see the 181 is the only meter that's able to read this. Let's go up a little higher. This is the upper limit of my function generator at 15 megahertz, and Again, you can see the 181 isn't having any trouble with this. But again, I think most people that are trying to make this measurement, they're going to be using a frequency counter. This is a circuit I built after watching one of Dave's videos. Essentially, there's 3 MOSFETs here, and they're switching a 10 ohm resistor across each one of these meters. The idea is essentially what we're looking for is how fast these meters settle. This is currently hooked up to our function generator. In the past, what I've done is I've used the frequency counter and the high-speed camera. I think what we're going to do for this is just go ahead and enable it. See, the BM786 is just a little slower. Than the other two, not by much. I'd say all real comparable. Really, I haven't ran into a lot of meters that I consider really slow. One meter that's particularly slow is the Gaussian Ultra. I think that was on par with Dave's 121GW. I don't know, I'd have to go back and look at the video of the two. I know I used both of those meters when I was demonstrating this. Let's just change over. We'll use this TPI meter. You can see how this thing kind of hunts around a little bit. It's like it switches to the lowest range and then it works its way up. Let's compare it against our little sum meter. A little bit faster. And this is with our Unity UT181A. Boy, it looks like the 2 meters are again very close. So yeah, all these meters that we're looking at right now seem to be on par with one another. So this meter right now currently has 2.02 firmware installed. I understand they have a newer version that may be a little faster than this. You can see how long that thing drifts for. If I slow down our function generator, watch what happens. You can see how the 121 continues to drift. Currently all the meters are attached in series and they're connected to my bench power supply. You can see we're outputting roughly 1.1 milliamps. All the meters are set to their microamp scales. Looks like they're basically reading the same values. Let's go ahead and we'll turn it up a little higher. Looks like we're at about 4.18 milliamps. Just over what the SEM meter can read. Let's go ahead and we'll drop it down. Again, this is a 40,000 count meter. So we're right at the edge right there, what that meter can read. What we'll do is bring on our other Brymen. And let's just go ahead and we'll measure the burden voltage for each of these. So it looks like the burden voltage for the SEM meter is 1.98. Looks like the Unity is 0.193 volts. Much better. Our BM786, 0.402. This is the BM786. Looks like it's the same as the BM786 at 0.404, 405. And again, this is the TPI. You can see it's also 0.4. And let's try our fluke. Again, 0.4. So by far it looks like our Unity has about half the burden voltage of the other meters, and it looks like the SEM is by far the worst. All the meters are currently set to their milliamp ranges, and you can see we're applying roughly 100 milliamp right now. Let's look at the burden voltage again. Looks like about 0.96 volts for the SEM. Looks like our unit T is about 0.38 volts. Our BM869S, 0.17 volts or so. Let's try the BM786, 0.25 volts. Not too bad. And this is the TPI meter. That is 0.146 volts. Let's call it 0.15. Slightly lower than what the BM869S is. Let's have a look at our fluke. And again, 0.173. Very good. Some of these meters are only rated for 400 milliamps. There's no reason to blow a fuse, so let's just run it a little lower. But again, you can see 333, 333, 333 and change. Same thing here, 333. Yep, so it looks like they're all basically reading the same value again. All the meters are currently set to DC amps. See, they're all reading basically 0.233. And let's go ahead and we'll turn up the current a little bit. Again, there's going to be a time limit on these, so we're not going to turn them up very high, but you can see we're at basically 5 amps. All the meters are essentially reading the same value. Looks like the SEM meter is reading about 50 milliamps hot. Let's have a look at our burden voltage now. We'll go ahead and we'll start with the SEM meter. And we can see it's 0.172. The unit T, 0.15. Try our BM869S, 0.15, 14. The BM786 looks like 0.1. Huh, a little better than the rest. Let's try our TPI meter, 0.133. And for a Fluke 198, looks like 0.25 volts. Yeah, so our new little Brymen meter seems to have the lowest burden voltage of all these when looking in the amps range. I'm just charging up a piece of plastic tube, and let's run it by these meters and see if there's any effect. Well, I wouldn't normally do this, but I ran into a problem with that Gossen Metrowatt Ultra, where that thing was so sensitive you couldn't even press the buttons on the front of the meter and get an accurate reading. I don't know if they ever fixed that meter or not. I saw the other day, I was on their website looking for something else, and they've actually changed the name of that meter, so it's no longer called the Ultra. It's got some other name now from marketing. And what's funny about it is they actually kept the same part number for the meter. So yeah, these meters, not sensitive to this. And you can see as I put my hand near them, nothing. Of course, the way I addressed that with that Gossen is I put a whole bunch of shielding inside of it. And that really helped. So that meter actually now works pretty good. Of course, that's a very expensive meter. I think I paid like $850 for it, but it's 300,000 counts too. So here I have our tape eraser. Again, that's caused problems with some of the meters in the past. I know Dave's meter was very susceptible to this. Let's just try it. I don't think any of these meters are real touchy. The Gossen again actually has latching relays in it, and I've had them change states, and then the meter won't actually display voltages. It's like, who comes up with some of this stupid shit they do? You can see basically no effect. Let's try it from the top. Different rotation. Yeah, and no effect. So it's good. Went ahead and measured the parameters for the continuity mode, and while I was at it I also measured it for the diode test mode, because both of these modes will flash the backlight and they also both beep. The big difference is the diode mode will display the voltage, where the continuity mode is going to display the resistance. So if we look at the open circuit voltage, The continuity mode is 2.285 volts, where the diode check is 3.173. The short circuit current for the continuity mode is 0.365 milliamps, where for the diode check it's 0.504 milliamps. The resistance that the meter detects in open is 308 ohms for the continuity and 200 ohms for the diode check. Now you see this note, this meter has what they call a short beep alert. Basically what happens is it changes the frequency as we change this resistance. So what I've done is I've measured basically where the resistance causes the meter to go full open, so it stops beeping altogether, and where it turns full on. So the short resistance for continuity mode is 270 ohms, and for diode check it's 190 ohms. The maximum frequency that the meter could detect with a 50% duty cycle was 15.7 Hertz and 1.1 Hertz in diode check mode. Then I also checked the minimum pulse width that the meter can detect using a 2 Hertz waveform, and I did not do that in diode check because it's already beyond this 1.1 Hertz. Actually, alias is back, so if I supply 2 Hertz, the meter's basically beeping at a 1 Hertz rate. But in continuity mode, it can detect as small as a 1 millisecond pulse. So the BM786 uses a 30 segment bar graph. This has an update rate of 50 times per second. Currently we're supplying a sine wave of 0.1 Hertz. One thing you'll notice, like with the TPI meter, see it updates that bar graph at the same rate that it updates the main display. Again, the Unity UT181, this is the only meter I believe I have where it can actually show both a positive and a negative value. So you can see it goes from a -6 up to a +6. What I've done is I've basically selected to drive up to 4 volts down to 0, so that basically prevents all the meters from auto-ranging. Again, you can see with the SEM, the display update rate is very slow, and they also update the bar graph with the display. So here we are at 1 Hertz, and you can see how bad that is now with the SEM meter. Notice how smooth it is with the Unity. Both Brymens are very smooth as well. Of course, again, we're sampling at 50 Hertz on a 1 Hertz wave. Again, the TPI, see how badly this is skipping. It's not as bad as the SEM, but again, it basically makes this bar graph worthless. You can see I've placed a little piece of foil on each meter. Basically, that's at the 4 volt mark. What will end up happening as we start to increase the frequency is a lot of these meters are no longer going to reach that 4 volt mark. So let's go on up to 2 Hertz. Here's the 869S. Here's the 786. The 198. And the TPI you can see is just skipping. This is currently at 4 Hertz. And this is at 6 Hertz. It doesn't look like the bar graph quite reaches our peak anymore. Both Brymens definitely do, and so does the 181. This is at 10 Hertz. You can see how the 181A is basically settled at 2 volts. Both Brymen meters look like they're still reaching the full scale. Let's have a look at our fluke. So yeah, similar to the 181, it's basically 2 ticks up, or about 2 volts. Let's go up a little bit higher. This is at 15 Hertz. You can see the fluke 189 is now fairly stable at 2 volts. Both Brymens though, you still get a feel for the peak. And the 181A, you can see now that's aliased, so we are seeing the peak again. Just want to get an idea. Here's the SEM. And here's our TPI. So yeah, it looks like the new meter is fairly fast. You'd expect that at 50 Hertz. All the meters shown here, except for the BM786, have an ability to interface these to a PC. The little SEM or the X-Tech branded meter, this has a RF interface. The Unity UT181A has a IR interface, and they supply the serial cable with the meter, but they also offer a Bluetooth interface for it. The BM869S, the Fluke 189, the TPI 194, all those are an IR interface only, and that's not included in the price of the meter, so it's a separate option. The wireless interface for the X-Tech is included. Again, that runs I think at 900 megahertz. It's a fairly simple interface. It uses FSK, where the 181 is using a BLE interface. Yeah, I'm sure by the time I edit this all down, we're going to be at least at a half an hour. So I think this is going to be the end of part 2. Depending how Brymen responds to my concerns about the AutoRange of the BM786, we may or may not run that big waveform test. For sure, one of the tests I'd like to do is look at the crest mode of this meter. Basically, what we're going to be looking at is how short of a pulse that this meter can capture. I may try to do some RF testing as well. And the other thing I'd like to do is go ahead and take it apart. Hopefully then we can get on to our destructive testing. Of course, I don't want to proceed to any of the destructive testing until I get an answer back from Brymen. Once we get through our transient testing, my plan is to go ahead and run the 50,000 life cycle test on the switch as well. So stay safe and stay tuned to the channel. There's a lot more to come. Later.